first talk, I'm going to give some more general properties about the comparison. And then the final talk, I'll try to focus on various examples and specific constructions and that sort of thing. So I'll just start with a combination of a reminder and a correction. Do you remember at the end last time? I defined S to be functors from e.g. local Artinian rings in non-negative chain degrees. Simplicial sets such that take A, B, and C. Look at this fibre product, f of the fibre product. Maps to the homotopy fibre product of FA, FB, and FC, and we require that to be a weak equivalence whenever the first map is a small extension. So that's the condition I gave you. There's an additional condition I forgot to mention, which is that we also assume that base field has to be contractible. So f of that has to map to something contractible. And if you don't have this condition, then your function just ends up being a lot of copies of the sort of functors you want to look at, potentially crossed through the topological space. Right, so now, okay, so I'm going to have a look at their tangent spaces. So if we look at for n positive, have a look at So we want to look at this loop space. So you remember epsilon n was where we just had a single variable in degree n. Look at the homotopy fibre product of 0 with 0 overlap. So that's the space of loops inside this space. And in this form, and then, well, that the same as this homotopy fibre product, where we replace the copies of 0 with fk, because fk is a single point. That's basically the point we were picking there. And now, as it stands, we can't apply that property because this map from K to this isn't a small extension, it's not surjective. But then what we can do is we say, well, we have an acyclic small extension this thing down to K. So this is just, this one just has just a complex where you've got one variable in degree n, another n minus 1. D is mapping from one to the other. So this is now something acyclic. We've got this acyclic small extension here. So that tells us that from So the second time I've managed to miss out. Last time I did give you two conditions, the third one is. So FA to F of B are weak equivalents. A to B and a cyclic. I think the moral here is that 3 conditions is too many. Always trying to define things with 2 or fewer. So we've got this condition here. So this thing is also contractible. And so over here with this diagram, we can rewrite this now as being equivalent to this curve. Stop writing that at the end of the board. That wasn't wrong, it's just going to appear on a new line. Start with this thing. And this now does map down surjectively here, where we just send epsilon n to epsilon n. Epsilon n minus 1 goes to 0. This is now in the form we're allowed to use. And this thing is just killing epsilon n. So the upshot of all that is that if we start from this space here, this loop space is this. Therefore, if I look at the ith homology group of this, sorry, the ith homotopy group of this is the same as the I plus 1 homotopy group. That I started with. And it's quite easy to see that these have an abelian structure. You see, we've got a ring homomorphism. And that gives, so this ring homomorphism here, which just does the obvious thing, gives us an abelian structure. F of this. And we can also multiply epsilon by scalars in K. So in fact, this thing's a K vector space. Then, because of that property we had down there, we can just define Hn minus I of F to be the ith homotopy group. Of K plus epsilon n. I then greater than or equal to naught. And the previous lemma effectively tells us that this is well defined. And similarly, so if I have a chain complex V, which is just got to be a non-negative change of reads. Back to spaces. Just to simplify the notation, I'm going to come out in the next lemma. So, n minus I cohomology group of F with coefficients in V is just defined by the same formula. So pi I plus V, and now we shift V by n. So if we took V as K here, we'd just get that again. So we're just generalizing that. And in fact, just by breaking this thing down into a load of one-dimensional copies, I should have said, it has to be finite dimensional, or this won't live in our category. So just by breaking this down into one-dimensional pieces, we actually get that this is isomorphic to Rx sum over all J H n plus J of F tensor H J of V. Just because you can, this is isomorphic to its homology plus something acyclic, and then you break off those bits one dimension at a time, and you get this. So really, I've just introduced this notation to avoid having to keep writing out things like that. So now, take a small extension.
If you're missing an I.
Oh, yes. N slash I. N minus I. So this is, yes. Yeah. Thanks. Maybe to make it simpler, maybe I'll rewrite the final circuit statement. What's there isn't wrong, but so now if we take a small extension. As we were working in with kernel I. Now, remember when we were constructing obstructions for these sorts of functors, we had B tilde as the code of I to A, and that maps down to B, so surjectively it's an acyclic small extension. And we also had that A sorry, what have I done? Too many K's. A plus I1. Sorry, I will wait eventually. We had that property there, and now we can see what that. So this tells us f of A is the homotopy fiber. Map for f of B tilde, which is effectively just a copy of f of B. This space. So on homotopy groups, we get a long exact sequence. The next term here is H1 minus N. And the sequence ends with pi naught f of b going to pi naught, sorry, pi naught f of a going to pi naught f of b going to H1 Fi. So it's allowing you to work out what these spaces look like effectively by carving them up into these small extensions. And there's a really simple corollary of that, which is that these cohomology groups detect weak equivalences. Actually, I should say with that long exact sequence, some of you will have seen tangent obstruction exact sequences you get in deformation theory, and that's sort of the pi naught and pi 1 terms of this sequence.
So the 0 degree is the tangent obstruction theory.
So the usual tangent obstruction theory is if A and B are, so usually it would be where A and B are just Artinian rings, and then it ends up stopping at pi 1, just because you get H1 and you get H0, and then H minus 1 is 0, so you end up with a 6-term sequence, or a 6-term sequence with or 7 if you count the initial 0. But this is a generalization of that, and it's a standard long exact sequence that topologists use all the time. Right, so now, so corollary. So a map morphism of these sorts of functors to weak equivalence, by which I mean the map from f of A to f of B is a weak equivalence, so an isomorphism on homotopy groups. Sorry, not f of A to f of B, f of A to g of A, for all f. If and only if it's inducing an isomorphism on cohomology groups. And the way you prove this, so you use small extensions. And the long exact sequence. What's happening is, for each of these small extensions, we have a long exact sequence like this for both f and for g. And these terms are all matching up. So once we know we have these terms matching up and these ones matching up, we deduce that these do, and that's our inductive step. Okay, so now I'm going to move on to explaining a bit more. Well, I suppose first of all, does anyone have any questions about this? And then okay, so now I will.
Yes.
Oh, yeah.
Another question. How do you interpret the Eiger terms when you, for example, the functor is a deformation of scheme.
On the scheme, so then what would happen is with, so this input, these would be DG Artinian rings,
Right.
and then those are, so the deformations are then some sort of derived scheme, and those are higher automorphisms of that derived scheme.
And the automorphism of the derived scheme.
Yeah, so it's higher automorphisms. So an example where you have seen things like this before is where, say, it's deformations of a chain complex, and then these things correspond to negative X groups. So it's that sort of idea. So it's well, I suppose actually another example you have seen where you do get these higher homotopy groups even on underived input was the example that Setterling started with of deformations in associative algebra coming from using the Frull-Hochschild complex. Because then what happens is, so you've got so pi naught is your isomorphism classes. Pi 1 in this case is just outer automorphisms. So it's automorphisms modulo inner automorphisms. So modulo automorphisms you get by conjugation by elements. And then your pi 2 consists of things in the center. So elements which conjugate trivially on things. Yeah.
Why isn't the abstraction space usually in H2 and dependent space in H1? What's
Okay, so this is the simple Hn of MCL.
Oh,
It's
okay.
as simple as that.
Yeah.
It's just because it's just the logical way of defining these is that you just look at what I've done here. The usual tangent space you look at is when I and n are both 0.
Yeah.
The obvious thing to call this is 0. But when you're doing this, you're getting H.
Yeah.
That's just. It's basically because Maracaton lives inside of L1. I suppose if we were working with shifted L-infinity algebras like Jonas, then this doesn't arise. And you don't have that shift. It's exactly that shift.
Yeah.
Okay, so now I'm going to try to explain a bit about how the comparison between these various things works. And I'm going to start by looking at, and this is something that Jonas has already looked at quite a bit, although we'll probably end up. Did you have a name for the functor from DGLAs to DG coalgebras?
I actually never said how this looks like. I just
No.
there was no name.
Okay, yeah. So it won't be conflicted with anything if I call this one beta and this one beta off the start. So is that okay? So this is DG co-commutative algebras. And there's a technical condition which I will put in, explain a tiny amount about later. Unich calls the condition being connected, which sort of follows on from Bullen's terminology. You can also think of it as incoinilpotent. It's basically saying that these are coalgebras that exist as subalgebras of sim V for some graded vector space V. Right, so the map beta is one you've already seen, where beta of L is, so it's direct sum. I suppose I'm going to have to make these co-unitals, so actually I'll just, so sim, yeah, sim n of L1 or minus 1. It's 1, I think. Yeah. Where you have a co-differential given on co-generators by this.
But if you write like this, you don't end up in co-nilpotent.
Oh, yeah, okay. And positive, yeah, and that, okay.
Yeah.
So then, yes, okay, so that just means I need to be a bit careful at one of the other equivalencies, but yes, that works better. Yeah, I'm less likely to make mistakes doing it this way as well. Right, so we have these, and we can, and then beta upper star is the left adjoint, and it looks very similar. So it's direct sum. Actually, it's just not another name. So you take the free graded Lie algebra, which I'm just going to call free Lie, and this is with graded conventions on C minus 1. And then the differential is defined on generators. And the differential on C, what's the code product? So we had because these are co-algebras, they have a code product. And in case you're wondering quite how these things match up, what's happening is we've got that mapping to that, and in fact, it's symmetric, so going to sim 2 C contained C tensor C. And the pedant in me can't help but say that really I should have said cosim because we're taking this as a subset rather than a quotient. But please ignore that comment. I just feel I have to say it. So looking at S2C, and then that means you have C minus 1 mapping to S2C minus 1, which we could write as, because shifts change sign conventions, alternating power of a shift means symmetric power, and you then double shift. So then we have to shift back once, and that's why this thing is degree 1. Yeah.
Well, so to go from Lie to co-commutative coalgebra, we look at the co-free co-commutative coalgebra.
Technically, the code-free in co-commutative Lie algebra, but yes. Sorry, I shouldn't have said that. Yes.
Why do we need nilpotency? Why do we need that nilpotency?
Okay, so this is forcing nilpotence by taking direct.
Here it is forced, but why in the other way around?
Oh.
What doesn't work if my co-algebra are not nilpotent?
Okay, and you can make this definition. It's just you end up with things on this side that I don't want to have to think about, and this construction will turn them into things I'm happy to work with, but it means this construction ends up being a sort of completion function. And in case anyone's wondering, so in general, the co-free co-algebra is something hideous intermediate between a direct sum and an infinite product. It's everything inside the infinite product on which you can sensibly define a co-product, which is not the whole of the infinite product. So, right, so we've got this junction here, and we've already seen it in disguise, because if I take a D-Artinian ring and I dualize its maximal ideal, I've got an object. So I get it. a co-commutative DG coalgebra. So put a factor from DG, sort of DGR, whole thing, not just plus of DGCC, where you just set A to the dual of its maximal idea. And then the multiplication here gives us a co-multiplication there. And so then we could look at what this adjunction gives us, and we have that Hom from does anyone want to tell me what this is going to be? Sorry, I don't mean that, I mean we need a beta there. So we have, the adjunction tells us these two things are the same. Does anyone want to tell me what that is? It's the Marikov factor. And so in fact, you could even think of an infinity algebra as being, so the category of L infinity algebra is a full subcategory of this category. So basically, an L infinity algebra is a code-free thing in here, together with the choice of coordinates, the choice of cogenerators. And now, the way that this ends up getting, so the way that we can then relate this to the sorts of functors that Manetti was looking at, of set value functors on DGR, is that it's a definition which I think this is Grothendieck's terminology, that there might be an earlier instance. So we say that he was working on a very much more general categories. We say a functor is left exact if it preserves finite limits. Equivalently, by the products and the final object to map to a single point preserves final products and the final object. And then to write maps DGR to set the category of exact functors. Now what happens is this is actually just the category of DG coalgebras in disguise. So we've got a map from DG coalgebras to this way. If I start from DG coalgebra back to the functor which sends Right. So you look at DG coalgebra harms from the dual of the maximal ideal to C. Or, if you prefer, and this is the way I tend to think about it, it's from the dual of C to that, except you have to take a sort of topological dual of this. And for those who know what this means, I won't dwell on it. This category here is how Krugman did constructed. Or, in fact, you prove this is the same as the pro category, the opposite. For those who know what it means. So this basically means formal inverse limits of things in here. So it's things like complete Noetherian, but the limits don't have to be indexed by countable indexing sets. So it's just, and then the reason this, and then what happens is that this is an equivalence. So that here is an equivalence of categories. And the reason is that every coalgebra is a union of its finite dimensional subalgebras. And so you end up, you can write each of these as sort of big filtered color limit of finite dimensional things.
So, do you mean the pro object of the opposite or opposite of the pro object?
I mean,
Thank you.
I mean that. Yes. Thanks. I should have. Yeah, so we've got this equivalence here. So we're saying that this category is the same as that. So if we think back to our diagram, so I've got beta mapping down to DGCC, and I've got this equivalence with these left exact functors. Anyone want to tell me what this composite map's going to be? So what was that? Yes, exactly. So this is just MC. Now that's to.
Is this equivalent only for DT plus R?
Oh, sorry.
It should be DT R.
Sorry, none of these pluses should be here at this point. Thank you. Yeah.
Otherwise, it's not true.
Otherwise, I need DG plus here. So I need a boundedness condition here, and then I don't have this functor anymore. Unless these are living in degrees 1 and above. Because of the shift. So if I did that, yeah. Now, okay. Yeah, so now what I'm going to do is show you. So what happens is these are, for those who know about model categories and so on, there's a model category structure on DGLAs in which the weak equivalence is a quasi-isomorphisms and vibrations and surjections. And there's also a model structure on DG coalgebras, but it's much nastier. In particular, the notion of equivalences is much more subtle. So basically what happens, and for the layman, what I'm saying is, we've got a notion of when a morphism of DGLAs is an equivalence, which is when it's a quasi-isomorphism. So when it's an isomorphism on cohomology, there is a notion of equivalence for DG coalgebras, but we have to use something subtler than that. And it ends up being the thing generated by duals of acyclic extensions, small extensions. And they don't actually generate all quasi-isomorphisms. And then similarly in this category, it's exactly corresponding to things generated by acyclic small extensions. And what basically happens is, those who do know about model structures, the cofibrant things in here are the ones where the underlying graded algebra is free. The fibrant things in here are the L-infinity algebras. And the fibrant things in here are the ones that map acyclic small extensions to surjections. So the pre-deformation functors in Manetti's language. So that's how those things match up. And now I'm going to show you how we can. So there's a notion of, whenever you've got a notion of equivalence, there's a notion of right-derived functors. So whenever you have some notion of equivalence, we get an isomorphism. So given a functor, I won't say what it's on. F, the right-derived functor. R of F is, and it's essentially unique. It's essentially unique if it exists. Under F, preserving equivalences. By under F, I mean we've got some natural translation from F to R of F. Now, am I almost out of time? It's like quarter past.
You have 45 seconds.
Okay.
You need to start something about that it's fun, because now it could be like trivial factor, right?
Oh, sorry. Essentially unique, universal factor. Yeah. So in other words, if I've got something else preserving equivalences, so that has to, essentially unique, universal factor. And now what happens is, so the right-derived functor of our Cartan to take that and then embed sets and simplicial sets, just setting a set to something with constant simplicial structure. Is exactly one hit achieved. And I will go a bit over time and explain why, because it's really quite nice. So the reason is that, so in DGLA, or you can rephrase this in any of these various equivalent categories, is so the right-derived functor of Hom is L. Sorry, write it that way. I'm from. So I said that MC was beta upper star MA to MA dual to L. So if we derive that, so this thing was MC. If we derive that, we get TLA, and the reason, just this proof to, so actually there are a couple of facts I should have mentioned by now. So one of these is that key facts. With this, the adjunction we had, beta upper star, beta L to L is always a quasi-isomorphism, and co-unit is also a weak equivalence. So opposite of it's slightly small. And that ends up meaning we could have worked this out in any of these categories. So now, the way this proof works is if you look in, it's paper by Dwyer and Kahn, but there's a very good account of it in Hovey's book. So if you want to work out derived functor of Hom as a simplicial set, so in general, you could say that Hom are derived functor of Hom, or what's known as R map, M to L, is given by at level n, you have Hom from M tilde to L hat n, where M tilde is cofibrillant replacement. And L to the diagram is really fibrant replacement. And most of you, all of these words will mean nothing, but DGLAs, that cofibrant condition just says it has to be, the underlying thing has to be free, which this already is. And that just leaves us trying to get something called a really fibrant replacement. And map from N to L tensor omega bullet delta N gives a really fibrant replacement. And for those who are interested, the reason that's true, the only properties you actually need of this simplicial object are that these things are all quasi-isomorphic, because they're all contractible. And so that's the easy one, and then the tricky one is that if you work out forms on the boundary of the n simplex, so you take forms on each face and glue them together, the map from forms on the n simplex is surjective. And so in particular, if you had any other diagram of DGLAs satisfying these properties, you could use them to construct this derived functor. And so the moral here, and I'm very bad at the time, is that You look at constructions like this, and it looks like something weird's going on, but the theory actually tells you that once you've chosen quasi-isomorphisms, you have no choice. This is just the right derived functor. This is just one presentation of the right derived functor. And the way that the way we then get from these to those set valued functors on DG plus art I was talking about is that if I stick a plus art in there and simplicial set there, I end up with simplicial DG coalgebras where the DG coalgebra is in non-negative cochain degrees, and then the correspondence is sort of total construction. And that's how we end up getting from that category S of those sort of Schlesinger condition type things. You can then get from one of them to a DG coalgebra, and then from that to a DGLA via this adjunction. That's how that works. So that's the end of this lecture.
Other questions?
Yeah.
So usually when you have a model category, if you want to compute the R home between two objects, it suffices to take either a vibrant or a co-vibrant replacement. Why is it that here we need both to be like vibrant and co-vibrant?
For the R home, you need the source to be co-vibrant and the type to be vibrant.
But that's not always true, right? Sometimes it's enough to take one.
Well, in most categories, so most of the ones you're used to, you'll find that all the objects are vibrant or all the objects are co-vibrant.
Oh, okay, yeah, okay.
But here it's been more convenient to, so you see all the objects in this category are vibrant, but it's more convenient to take really vibrant replacement of L than to try really co-vibrant replacement of this thing.
Yeah. Oh, okay.
So if you, we already had something co-vibrant here, so it was easy to leave that alone and fill around with this.